Alrighty, guys, welcome back. This is going to be section 3.5 for Algebra 1, transformations of linear functions. So we're going to learn about three kinds of transformations today: translations, dilations, and reflections. So all three of these are just going to be ways to kind of manipulate a graph, and we're going to focus only on straight line graphs for now. Later in the year, you'll see we'll do these same three transformations to other kinds of graphs. So transformation, first of all, is just any kind of change to a graph. Then the three categories we're going to do are translations first, which means sliding the graph left or right or up or down. So the shape and the visual features of the graph look the same, just where it's located is going to be a different spot. A dilation is a fancy way of saying stretching or shrinking. So you leave it in the same location, but you stretch it out taller or shorter up and down, or you stretch it out taller or shorter side to side. And then a reflection is just like in a mirror or in a lake. You take something that's in one spot and you reflect it over a line. Maybe it goes from being right side up to upside down, or maybe it's on the left side and it reflects over to the right side, something like that. So we're going to look at each of these three in detail in the coming couple of slides. So here we go. So first one, translations. There's four different ways that you can translate because there's four directions on a coordinate plane. Up and down are two of the possibilities, and left and right are two of the possibilities. So we're going to look at each of these four. It looks more complicated than it is, if we're being honest. And I'm going to show you on Desmos after this exactly how to implement these. So if you have any function, f of x, and you just simply add a number to the end of it, that's going to take the graph and just move it upward. So let me give you an example. Say you just have y equals x, and then you change that into y equals x plus 3. It's going to have the same graph, just literally moved up 3. So instead of starting at 0, 0, it's going to start up at 0, 3. Same thing if you subtract, then it's going to move it down. So right here it says if k is bigger than 0, that means you're adding a number. And then over here, it says f of x plus k, but then it says k is negative. K is less than 0. So to be honest, I personally like to write it instead like f of x minus k, because you're subtracting an amount and that's making it move down. But an example would be like if you take the same graph and you write y equals x minus 5, say, that means you take the graph and you move it down 5 units. So it's going to start with a y-intercept at -5, and the whole graph is just shifted down by 5. So those are up and downs. All you do is you add or subtract to the end of the equation. Now, on the other hand, a horizontal translation, because that's on the x-axis, not the y-axis, this is going to require a change to the x variable itself. And it's a little bit counterintuitive at first, but I'll try to explain it well. So f of x minus h. So that means whereas you used to have an x, you replace it with x minus h. And if h is positive, that's actually going to move the graph to the right. You might be thinking, what the heck? Why is a negative going to move it to the right? So the reason a negative moves it to the right is because 0 is a solution to the blue line. And if, let's just say this is a coordinate point like 2. If I put x minus 2 in parentheses, and I ask you, what value of x is going to make this whole function 0, you can see the answer is 2. So at the location x equals 2, which is right here, you get x minus 2 as the expression that has a solution of x equals 2 to give out an output of 0. Because on the y-axis, we're not going up or down at all. So this is the coordinate point 2, 0. I hope you can see that. So the net effect of all of this is just if you replace x in your equation with x minus a number, and we'll call it h, then your graph is going to move right by a distance of h units, whatever that value of h is. And h is, in this case, positive. And the same thing is true to go to the left. It's going to just be the opposite sign. So if you replace x with x, I'm going to put here x plus h, because that's what it's actually going to look like when you see it written down. This is going to move left by h units. And again, the way that you can kind of think about is, imagine you're looking and you're saying, hey, okay, if I see an actual example like y equals parentheses x plus 4, and I ask myself, what value of x is going to make this whole thing 0? Well, obviously it's going to be -4. And -4 means left 4. So you can see that the direction the graph is moving is kind of the opposite of whatever you see symbolically with this value. If it's positive, you're actually moving to the left to cancel it out. And if it was negative, you'd be moving to the right to cancel it out. So again, we'll explore these in more detail, but that's a nice little introduction, hopefully. So next one here is dilation, so stretching and shrinking. So to stretch a graph out, you have to make the entire thing bigger. So if you want to make it vertically taller, you multiply the entire graph by some number bigger than 1. So here's the equation f of x, and it shows we multiply the entire equation by a number, and that number has to be bigger than 1 if we want our graph to stretch out and get taller. Likewise, we take our function, our entire equation, and we multiply it by a number between 0 and 1, so something smaller than 1, in order to make the whole graph get shrunken down. And all we're doing is we're saying the y value, or the height of our function, is going to be less than it used to be if we multiply by a number smaller than 1, and it's going to be bigger than it used to be if we multiply by a number bigger than 1. So both of these, I hope, kind of make sense. So like y equals 2x is a vertically bigger, stretched out version compared to y equals x. All the points on y equals 2x are going to be taller than they would have been on y equals x. And like y equals 1/3 x is going to be shorter than y equals x. All the points are going to be smashed down and compressed and at a lower height than they used to be. Now, a horizontal dilation is the same thing but side to side. So you're either compressing side to side or stretching out side to side. But the problem is our functions are written with the y-axis as the output value. So like y equals some function. So to change side to side is not quite as easy. Instead of changing the entire function, we just change the x variable itself. So you change the input and you either stretch or shrink that input. So if you have an input value that's bigger than 1, then the graph is going to be compressed. So let me show you what I mean. Like, so say you have y equals x, and I change that to y equals 3x. So a smaller x value is going to achieve the same results. So this function is going to get horizontally compressed. So smaller x values get you to the same place that you used to be. Right here, x has to equal 1 in order to get y equals 1. But here, if x equals 1/3, then y equals 1. So I'm getting to a height of y equals 1 much more quickly. I'm achieving that in a compressed time frame, or in this case, a compressed x-axis frame. So everything is getting smashed in closer together. And you might be looking at this saying, wait a minute, Morgan, y equals 3x. Couldn't I have just written that without parentheses and said y equals 3x up here? And then said, hey, that's a vertical stretch. So it turns out that with straight lines, horizontally compressing something or vertically stretching it can often have the same result. So yes, compressing it horizontally and expanding it vertically often look the same. And if that's the only change that happened, in fact, they're identical. If you start mixing some stretching and shrinking with sliding the graph left and right and up and down, sometimes they're not interchangeable. But if the only thing that you're looking at is a stretching or shrinking, then a vertical stretch is identical to a horizontal compression. And likewise, a horizontal expansion is the same as a vertical compression. So if you plug in a number with the x that's smaller than 1, the graph is going to stretch out. Again, I'll show you in Desmos all of these things afterward in like a kind of interactive visual way. But for now, we kind of just want to take down in our notes, maybe write down this key block for each of these 4. In this class, in Algebra 1, to be perfectly blunt with you guys, we're going to focus almost exclusively on vertical dilations, which I think are much simpler to kind of understand. And then you'll focus more on horizontal stuff a little bit this year. We're introducing it, but you'll focus a lot more on these in Algebra 2 and especially in pre-calc. So a couple of years down the road from now. All right, moving on to our third and final one, which is going to be reflections. So with reflections, we are taking some graph and we're having an axis that we kind of bounce everything across. So if you reflect something across the x-axis, let me change color here. Let me choose red, perfect. So if you reflect something across the x-axis, then imagine this dotted line. this coordinate up here becomes this coordinate down here. This was a positive y value, and this is a negative y value. So all you have to do to reflect something from the top to the bottom is, you can see right here, what pops up is a negative sign. So if you put a negative in front of the entire equation, it's going to reflect the equation from wherever it was in the positive side down to the negative. And if it was negative, remember that a negative times a negative reflects it back up to the positive side. So a negative in front of the entire function is going to reflect it vertically up and down. So if I have y equals, say, x plus 3, and I change that into y equals, now this is important, I got to put parentheses around the entire function. So now that negative there is a reflection over the x-axis. So it takes the graph and it flips it up to down, down to up. So reflect over x-axis. Okay, to reflect side to side, you can look at what's changing. This point has a positive x value, if we look here on the x-axis. And then the point that it's reflected onto has a negative x value. So when we compare what's changing in this function, we can see that the input here was x, but the input down here is a negative x. So instead of putting a negative on the entire equation, you're only putting a negative on the x value itself. So for example, if I have y equals x plus 3, let's use the same example, and I write y equals negative x plus 3. The key difference here is because I'm only putting the negative on the x, not on the entire function, then this is going to be a reflection across the y-axis. And like I said, we'll see this in Desmos, and we'll see lots of examples coming up on the next slide. So these two reflections are possibilities that we'll look at right now. X-axis reflections change the y-coordinate or the output of your function, and y-axis reflections change the x value or input. And if you're ever, you get these two mixed up, just draw a little picture and you can easily see that if you reflect top to bottom, you're changing the y-coordinate. And if you reflect side to side, you're changing the x-coordinate. Okay, so I want to take a quick pause and go over to Desmos. Let's click here, click here. Okay, so we'll take a quick pause and we'll look at Desmos. And I've written this graph y equals x. So I want to show you what happens when I put a plus like 3. The graph just moves up 3. And in fact, let me bring back the original. So you can see that the red line is exactly 3 units higher than the blue line. And in fact, instead of putting a 3, I can put a k there and add a little slider. And as I make this bigger, you can see the red line is moving up. And if I make k negative, the red line moves down. So this is a vertical shift up or down. The red line is moving up or down. Okay, now let me take that one away and let me put in y equals parentheses x minus h. Okay, and then add a slider. Now, when h is positive, it's moving to the right, but that's because I have a negative sign in here, okay? And if it's negative, it's moving to the left. But let me instead say, for example, if I put in just an actual number instead here, if I say x minus 4, you can see the line is actually to the right 4. So when you put in a negative here, it's moving to the right. And if I put in, let's say like plus 2, it's moving left 2 over here to negative 2. And again, you might notice that as I fluctuate, let's go back to the one up here. As I fluctuate this k value, when you see this like on the graph moving up and down, if you look at the x-axis, it looks like it's moving side to side. If you look at the y-axis, it looks like it's moving up and down. And like I said, with straight lines, these kind of are interchangeable. Up and down and side to side can more or less have the same impact. But when we look at other different types of graphs, then there will be a more clear difference between up and down and side to side. Okay, the next one we can quickly look at is if I put a number in front. So instead, let me put an a in front and add a slider. So if a is a big number, it's getting steeper and steeper. It's getting vertically stretched. And what happens if a is the number smaller than 1? It's getting flatter and flatter. It's getting compressed. And what happens when a is negative? Oh, it got reflected completely downward in the opposite direction. So now there's a negative slope. So if you're not sure about these things, just drawing a simple equation in Desmos is a great way to kind of explore them a little bit. And we'll be doing a lot more in class, obviously, but hopefully this kind of cemented the idea for you a little bit. Okay, we'll come back over here and we'll do a couple of examples and then we'll be all set for this video. So here's our examples that we're going to solve together. State the change from the parent function. So here's our parent function. In all cases, it's just going to be g of x equals x. That's the parent function for a straight line. So a -5 at the back means down 5. A 1/6 in the front means shrunk or compressed. Shrunk to 1/6 of the original size, or compressed to 1/6 of the original size. A -14 at the back is going to mean down 14. A -8 here, this is in parentheses. So now we're looking left and right. So this is going to be right 8. And again, this one is a little bit counterintuitive. It's the opposite of what you see. You see a -8, but it's right 8 because you would have to plug in 8 right here to get 8 minus 8 to cancel it. So a +8 that would be plugged in would mean that you moved right 8. Okay, and now this one has 2 changes going on. So this part right here is telling us to change left and right because it's in parentheses with the x variable. So this is left 9. And this is a number smaller than 1. So it's shrunk to 0.2 of the size. So it's going to be 5 times smaller because 0.2 is same as 1/5. So it's 1/5 as big or 5 times smaller. That should say left. Okay, this one here, +5 at the back without any parentheses is going to be up 5. And a 3 in the front is going to make it taller. It's multiplying it by 3. So it's going to be 3 times taller, or stretched by a factor of 3. And this is a vertical stretch getting bigger here. Okay, how can we take these graphs and look at it the other way? How do you create an equation if you know the graph? So one thing you can do is you can just look at, is it moved up or down or left or right? Is it changing the slope or not? So this one looks like it has an intercept at like -2.5. But the slope is still up 1 over 1, up 1 over 1, up 1 over 1, etc. So this would be y equals x minus 2.5 because it's moved down 2.5. I could have also looked at it from a perspective of changing the side to side. So instead, maybe I look at it and say, okay, I want to look over here and say it's moved to the right by 2.5. So if I have a change to the right, I put in parentheses x minus 2.5, and that's going to be right 2.5, whereas the other one was down 2.5. But obviously, if you look at these, hey, they're the same exact equation, which makes sense because if it's a given line, it can only have one right answer. All right, let's look at the next one. So this one, it looks like it's been moved up. If I look here to 1.5. But it also looks like it's been flattened a little bit, right? So instead of going up 1 over 1, it looks like I only go up 1/2 over 1, or easier is up 1 over 2. So there's a shrunk, it's been shrunk to 1/2 of its original size. So I could just say y equals 1/2 x, so it's shrunk, and then it's up 1.5. So that would be a way to write the equation. So look, is it stretched or shrunk? Is it reflected or not? And is it slid up or down or left or right? Okay, that's it for this video. I hope you guys found this helpful, but certainly in class, we'll have lots of opportunities to go over these, to ask questions, etc. All right, see you in class.